this video, we'll discuss limits at infinity and horizontal asymptotes of other functions. This type of function is very common with our limits at infinity homework problems. So we'll look at this example. We'll look at a very similar slight modification of that example, and then a third example that's similar. And then we'll look at some other functions. Primarily those that we're interested in will involve quotients. And this particular one is very common, where you have a function involving a rational exponent or a radical in the numerator or denominator and a polynomial in the numerator. This would have a tendency to look similar to a polynomial, but the radical changes things a little bit. We're also interested in these types of functions that might involve the sign, other trig functions, logarithmic and exponential functions, and we might be interested in their end behavior as well. So again, we're looking at these, 6 examples, and we'll look at them on Desmos.com. So first we'll look at this function h of x, where we've got 4x squared minus 3x plus 1 in the numerator. That's just a polynomial. It's a second degree polynomial. So the graph would be the graph of a parabola. It might look like this. And then in the denominator, we have this function, which is a composite function involving a polynomial and a square root function. So it looks like that. Kind of interesting. It's actually got 2 pieces. Probably whenever this expression under the radical is negative, we're going to have an issue. We can't take the square root in the real number system. So we would get complex answers. But outside of these bounds, it looks like from x equals from negative infinity to negative 2.92, and then from this point to infinity, it looks like negative 1 to infinity. We've got positive values, so we can take the square root of those answers. But h of x is actually the quotient of those 2 functions. So it looks like this in general. Now you might look at that and say, well, it looks like the y values are approaching a finite number. They seem to flatten out, and I think they're approaching whatever the value is given by that second tick mark on our y-axis. And it's a little bit hard to see. If that's 10, this must be 2, 4, 6, 8. That must be y equals 4. So if we look at that, we graph the line y equals 4, we can see that the function gets very, very close to the line y equals 4. You might say, like, how would I be able to determine that without a calculator? I'll show you how to do that on the paper in just a moment. So let's do that on paper now. So we're here, and the graph suggests that the answer is 4. The limiting value as x goes to positive or negative infinity is 4. So you might say, how do you find that algebraically? How could we determine if that was the result just by looking at this function? Well, notice that the numerator has a leading term of 4x squared. So that tells us that our polynomial is going to be a parabola when we graph it. And then look at the denominator. We saw that this was a composite function involving a polynomial and a radical. And we're going to have problems whenever the expression under the radical is negative, because we can't take the square root of a negative number in the real number system. But outside of a particular interval, the expression under the radical is positive. This x to the 4th dominates over the x cubed as x gets very, very large, either large and positive or large and negative. If I have 1,000,000 and I raise it to the 4th power, it's a very, very large positive number. And if I take a negative 1,000,000 and I raise it to the 4th power, those negatives cancel in pairs. So we end up with a positive number. So this is going to dominate as x gets really large. So we would expect a result that looks something like this 4x squared divided by the square root of that x to the 4th. Well, the square root of x to the 4th is x squared, so I would expect the limit to be 4. You might say, how can we prove that algebraically? Well, we're just going to do the same thing that we always do. We divide by the highest power of x in the numerator, or excuse me, in the denominator. But we have to think about what that would look like in terms of this square root. The highest power of x in the denominator is actually, if we just look at this term by term, be this x to the 4th under the radical. So I'm going to divide everything by x to the 4th. And I can do the same thing in the numerator. I'm dividing by the square root of x to the 4th as well. But when you do that in the numerator, you want to remember that the square root of x to the fourth is actually x squared. So you get this. We end up with 4x squared minus 3x plus 1, all divided by x squared. And then under the radical, we're dividing each of those expressions by x to the fourth. X to the fourth over x to the fourth is just 1, and then we've got 3x cubed over x to the fourth, which is just 3 over x, plus 2 over x to the fourth. And still just simplifying. The square root of x to the fourth is x squared, so we've got the 4x squared over x squared is just 4. And then if we divide each term by x squared and simplify wherever possible, we get this. And so we get 0 here because -3 over a large number is going to be a very small number. And 1 over a large number squared is a small number. This goes to 0, this goes to 0, and this goes to 0, and this goes to 0. And that happens whether x is positive or negative. If I have -3 over -1 million, the negative and the negative give us a positive number, but it's a tiny positive number because I'm taking 3 and dividing it into a million pieces. So it's very small. And so this is small, this is small, this is small, and this is small, and we just end up with 4 divided by the square root of 1, which is 4. And since the limit is a limit at infinity plus or minus infinity, that tells us the graph has a horizontal asymptote. Or the function has a horizontal asymptote 4. So y equals 4 is a horizontal asymptote of that particular quotient function, as we saw on Desmos.com. But we have to be careful about this. We know that the square root of x to the fourth is x squared, and that works because if I take a positive number and I raise it to the fourth power, I get a positive number, and I take the square root of that positive number, it's still positive. And the same is true, and if I take the x to the fourth and I take the square root in general, I get x squared, which is just positive. So these are equal to each other all the time. It does not matter what x is. This is true for all x in the real numbers. Any real number, this will work. But things change a little bit if you have something like this, the square root of x squared. So let's look at a similar example. I'm going to call this example 1 star. I want the limit as x goes to positive infinity of 4x squared minus 3x plus 1, all divided by the square root of x squared plus 2. Now I want to divide by this highest power of x in the denominator. The highest power of x under the radical is that x squared, so I'll divide by x squared under the radical. I can do the same thing in the numerator, as long as I remember to divide by the square root of x squared, not just the x squared. Now we have to be careful here because the square root of x squared, you might be tempted to say that that's equal to x, but it's not always equal to x. If I took -2 or -3 and I squared it, I'd get 9. And then the square root of a 9 would be positive 3. I think I may have said that wrong. If I take -3 and I square it, -3 times -3 is positive 9. And the square root of 9 is positive 3. So if I put in a negative number, the output is still positive because I'm taking a positive square root. It turns out that in general, this is going to give you the absolute value of x. If x is 0, we get 0. But if x is negative, we're taking it, we're squaring it, and then we're taking the square root. So we always get that absolute value. Now, as x goes to infinity, the absolute value of x is just going to be equal to x. So dividing by the square root of x in the numerator and the square root of x in the denominator is fine. We're dividing by the same thing. But in the numerator this time we're dividing, that's the same as just dividing by x. It's the absolute value of x in general, but x in this case. X squared divided by x squared under the radical is 1. And then we've got that down there. And then if I divide each term in the numerator by x, I get 4x minus 3 plus 1 over x, all divided by this expression here. So now I want to think about what happens as x goes to infinity. Well, 1 over x approaches 0, because 1 over a large number is a very small number, and 2 over x squared is also going to 0. And I end up with this 4x minus 3 divided by 1. Well, as x goes to infinity, 4 times a large number is a very large number. So the answer is infinity. That means the function does not have a horizontal asymptote. But notice that as x goes to infinity, this term disappears and this term disappears. So our function is actually approaching the line y equals 4x minus 3. Let's look at that on Desmos.com and graph the line y equals 4x minus 3 and verify that that's what we get. So I'm taking that first example and I'm changing the denominator. Under the radical, we've got x squared plus 2. And from our calculations, we said that it looked like the function had a slant asymptote y equals 4x minus 3. It's a little bit hard to see. Maybe we need to stretch things in the x direction a bit. So basically, I want to change my window so that my x values are perhaps between like negative 14 and 14. So it's not going to be to scale anymore, but it's going to be a little bit easier to see kind of what's going on. Oops. There we go. Still difficult to see, but we can tell that that function is approaching the line y equals 4x minus 3 as x goes to positive infinity. Now you might look at this on the other side and say, well, it's a different line over there. But I would also expect that I look at this purple graph as x goes to infinity, y goes to infinity. So it doesn't have a horizontal asymptote, but it has that slant asymptote. And then on this side, it looks like it has a different slant asymptote. And so let's do some calculations on paper and think about what happens as x goes to negative infinity. So now we've got the limit as x goes to negative infinity of the same function. Now pretty much everything is going to be the same. But we have to think about what the absolute value of x is as x goes to negative infinity. Well, if x is negative, we take that negative number and multiply by -1 to get the y values on the absolute value graph. The negative of -3 is +3. So the absolute value of -3 is +3. So this is always going to give us a negative or a positive number when we multiply by the -1. So we're doing the same thing that we did before, but we have to remember that when we simplify this expression, we're actually dividing by -x. And in the denominator, we're dividing by x squared term by term, just as before. So we get the limit as x goes to negative infinity of 4x squared divided by -x, and then -3x divided by -x minus 1 over x, all divided by this expression right here. As x goes to negative infinity, we've got -1 divided by a large negative number. It's going to be a tiny positive number, but it's tiny. It's getting closer and closer to 0 the larger that magnitude becomes. So that goes to 0, that goes to 0, and we get a very large negative number times a -4, which is going to go to positive infinity. So the function does not have a horizontal asymptote. But it does have a slant asymptote again. The function that remains as x goes to negative infinity, after we simplify those terms that are very, very small, is that y equals negative 4x plus 3. So let's look at the graph. So that was our asymptote for the as x goes to positive infinity. One as x goes to negative infinity is very similar. We've got a negative sign there and a positive sign there. And it's consistent. It looks pretty much the same. The function is approaching that line as x goes to negative infinity. And we can see that the y values go to positive infinity. All right, I think I made a mistake. I forgot to resume recording as I was doing this example. This is example 1 double star. We said, okay, I've got a linear function in the numerator now, 4x plus 1. And I still have that square root of x squared in the denominator, square root of x squared plus 2. So we divide by x squared under the radical. That's legal as long as we do the same thing in the numerator. And then we just have to keep in mind that that is the square root, or the square root of x squared is always positive, because whenever you take the square root of something, it's a positive number. So we get the absolute value of x rather than x. As x goes to positive infinity, we've got 4x plus 1 divided by x, which is 4 plus 1 over x in the numerator. And as x goes to negative infinity, on that branch of the absolute value graph, x, or the y values are equal to negative x. So we'll be dividing by negative x, which just gives us a negative 4 there and a negative 1 over x there. After we evaluate those limits and simplify the denominator, you just get 4 plus 1 over x divided by the square root of 1 plus 2 over x squared. This goes to 0 and this goes to 0 as x goes to positive infinity. And you get 4 divided by the square root of 1, which is 4, as x goes to positive infinity. And then when x goes to negative infinity, you just add that sign there, which adds a sign there and there, which gives us a negative 4 divided by the square root of 1, which gives us a negative 4. So let's look at that graph on Desmos.com now. All right, so here's our new function, and here are the horizontal asymptotes y equals 4 and y equals negative 4. It's kind of hard to see, but you can tell that the graph is approaching both horizontal lines. As x goes to negative infinity, we approach negative and 4, and as x goes to positive infinity, we approach positive 4. But we might want to exaggerate some of the features by changing the dimensions for the y-axis. We see the y values go between, looks like, well, negative 4 and 4. So let's let the y's go from negative 5 to 5. And then you can see it that here our y values are a little bit greater than y equals 4, but they're approaching our asymptote. And then over here, our y values seem to be a little bit greater than y equals negative of 4 and approaching that asymptote. So we get different asymptotes on each side. And that's because of that square root of x squared. All right, so we've taken a look at these examples. All of them involve that square root of x to the 4th or x squared or something like that. Remember, you're going to have different behavior on the left and the right. Occasionally, in some cases, and you really just have to look at this expression. If there's a radical involved, if you have an even root, a square root, a 4th root, a 6th root, or something like that, the answer is always positive. So you have to write that expression in terms of x as a positive number. So the square root of x to the 4th is always x squared, which is positive, and it's fine. But the square root of x squared is the absolute value of x. And that's positive when x is positive, or the answer is always positive, but that's equal to x when x is positive, and the opposite of the negative number x when x is negative. And so you want to keep that in mind. Now we might also be interested in these limits as well. If the limit is x goes to plus or minus infinity of sine of x divided by x. Now, when I look at this, I just think, okay, sine of x is oscillating between -1 and 1, and it oscillates in a very regular way. And then we take it and we divide by a very, very large positive number. Well, I take some number that's negative, or oscillating between -1 and 1, and is going to positive infinity in the denominator. Well, that finite number divided by something very large is going to be something very small. So I would say that answer is 0. So y equals 0 is a horizontal asymptote of this function. As x goes to negative infinity, we're going to have a number that's oscillating between -1 and 1 divided by a very large negative number. But dividing by a large negative number, taking a number between -1 and 1 and dividing by a large negative number is also going to give us 0. So that's going to be y equals 0 as our horizontal asymptote as x goes to both positive and negative infinity. Now at x equals 0, we get sine of 0 divided by 0. That's a 0 over 0 indeterminate. And we will look at that limit in a bit. See what happens as x goes to 0. But let's look at the graph and verify that this is our horizontal asymptote for this function. Here we've got a sine of x in the numerator, which looks like this. An x in the denominator, which is just our standard linear function, and we're taking the quotient. This number oscillating between -1 and 1, divided by a number that's going to positive or negative infinity as x goes to positive or negative infinity. And we sort of see what I was just talking about. I've got a number that's sort of fixed in that finite interval, and I'm dividing by something very large, either large and negative or large and positive. So the horizontal asymptote is y equals 0, which is just the x-axis. If you want, you can graph it with a dotted line. One of the things that's interesting to me about this graph, though, is when I plug in x equals 0, the denominator is 0. But if I plug in x equals 0 to the numerator, we also get a 0. So we've got a 0 over 0 indeterminate form there. But it looks, so the function's not defined, but it looks like we've got a finite limit. And if we just look at the tick marks on the graph, each of these boxes represents 1 unit. So it looks like the limit is 1. We're going to prove that in a different video. We might want to exaggerate the features a little bit by letting the y values go between, I don't know, let's say 0 or negative 0.5 and let's say 1.5. Then we have a better sense of what's going on. Notice that this function is 0 a lot of times. It's going to be 0 every time the numerator is 0, which it means it's going to be 0 at all of the multiples of pi. So to emphasize that, we might want to increment in intervals of pi. So it's 0 at pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, and so we can see that now. But that's our graph. Notice also that the graph is a little bit misleading if you zoom in at x equals 0, it's a little bit hard to see, but the function is actually undefined at x equals 0, y equals 0, but the limiting value is 1. We will prove that in another video. But we can see that the end behavior as x goes to positive or negative infinity is 0. So the horizontal asymptote is y equals 0. Now this example, this next example on paper is a little bit more challenging. I just made this up. I said, okay, I've got a polynomial x squared plus 4 in the numerator. I'm dividing by the natural log of the absolute value of x. And I'm interested in the behavior as x goes to positive or negative infinity. Well, a couple of things that we know. X squared plus 4 looks like this. It's just the graph of y equals x squared, shifted up 4 units. And natural log of the absolute value of x looks like this on this side. when x is positive, it looks just like a log function. But then when x is negative, it looks like that reflected log function. We actually have to plug in negative x values over here. And then we can take the log of those negative x values. And so you've got the same thing on both sides. It's just reflected. You're just saying to yourself, okay, if I take these numbers and I divide by these numbers, what should I get? And I think I should be getting plus or minus infinity. Oh, wait, actually, no. Let's look at the limit as x approaches infinity first of x squared plus 4 over natural log of x. Well, this is a very large number divided by a large number as well, but x squared is growing much faster than the natural log function. So the result should be infinity. As x goes to negative infinity, these y values are positive, but these y values are positive as well. As x gets large in magnitude, but farther more negative, when we take the absolute value, we're still taking the log of a very large number, which is going to be a large positive number. So we get a positive number divided by a positive number, and we should get a positive number. So we should get positive infinity on either side. I think I said plus or minus infinity, but that doesn't sound right. Trying to think about why that might be different, but okay. So now let's look at the graph on Desmos.com and see if the graph is consistent with what we just talked about there. So here are the graphs of y equals x squared plus 4 and y equals the natural log of the absolute value of x. Now in Desmos, it won't allow me to graph just the natural log of the absolute value without specifying the domains. So remember, the absolute value of x is x when x is positive, and it's negative x when x is negative. And so I graph it in branches, and then we see we're going to have a positive number divided by a positive number and a positive number divided by a positive number on either side. So now if I graph the corresponding quotients, I get something that looks like this. Look at that. It has some interesting branches there. So this says I have x squared plus 4 divided by the natural log of x. And I would imagine that the result goes to infinity. And it looks like it does, but it looks like it has this sort of weird branch here. Let's think about why that is in a bit. And then on the other side, we have something very similar. It's symmetrical. So I've got 2 branches there as well. Let's think about why that might be true. And I think to think about why that might be true, it says, well, when are we going to have a problem? When is the denominator equal to 0? Well, it's equal to 0 whenever the logarithm is equal to 0. And we know the logarithm is going to be equal to 0 when x is equal to positive or negative 1. Because the natural log of 1 is 0, because e to the 0 power is 1. And the natural log of the negative of negative 1 is just the natural log of 1 again. So we get 0 because of the symmetry. We're going to have a 0 in the denominator whenever x is plus or minus 1. So that means we're going to have vertical asymptotes at x equals plus or minus 1. So let's graph them. And that makes sense. It's consistent with what we see. Now, it looks like there might be a slant asymptote, but I'm not sure. Curious. I'm curious about how y equals x looks compared to this, compared to these. Doesn't look like that. Y equals x squared. It doesn't look like that either. I guess it doesn't have a slant asymptote. Now, it kind of looks like it might, but maybe that's just because this y scale is not does not have the same sort of dimension as the x scale. 1 unit in the x direction is like this, and 1 unit in the y direction is like that. And that's just a choice. That's just because of the minimum and maximum value that we used for our x and our y here. Desmos does that automatically. We can adjust it if we want to, if we're interested in particular features of the graph. But in this case, if the dimensions aren't the same in the x and y direction, it's just we're not seeing any particular function that this quotient is approaching as x goes to positive or negative infinity. So we looked at that. Now let's look at this one. Now this one, you might be tempted to treat this the way we treated these functions. You want to divide by, or in the past we've divided by the highest power of x in the denominator, because we're trying to simplify that denominator as much as possible. We want to have just a finite number in the denominator that doesn't go to 0, it doesn't go to infinity, it's just finite. Now we're going to do something similar here. We have to think about which functions dominate, or which functions are largest as x goes to infinity. Well, obviously, e to the x, an exponential function, grows much faster than y equals x. So we'll graph those functions, e to the x and y equals x. We see that the e to the x term dominates. And if it dominates, that means when we're trying to simplify this, we're going to have we're trying to evaluate the limit, we're going to get an infinity over infinity in determinate form, because this function goes to infinity and this function goes to infinity. But we can get rid of that infinity over infinity in determinate form, or at least as x goes to infinity, that's true. We get rid of that by dividing by that dominant function. So let's do that. The limit as x goes to infinity of 2 e to the x minus 1 over 4 e to the x plus x. And e to the x grows faster than x. So we're going to divide by e to the x here and here. Two e to the x divided by e to the x is just 2. And then we've got 1 over e to the x. 4 e to the x divided by e to the x is 4. And then we've got x divided by e to the x. Now this one is a little bit harder. We're going to look at that this quotient later when we study L'Hopital's rule. But this one is a little bit easier to see. As x goes to infinity, e to the x is obviously very large. E is just 2.7-ish, right? And we raise it to a large power and it's still a large number. 1 divided by something very large is very small. And here you've got something that's going to infinity and something else that's going to infinity. Because this term dominates, or this function dominates, we get 0. We haven't really proved that yet. We can look at the graphs and sort of convince ourselves that that's true, but we'll prove that when we learn L'Hopital's rule later in the course. So after we do that, we get these two terms go to 0. You get a 2 over 4, which is 1/2. So y equals 1/2 is a horizontal asymptote of this particular function. Now let's look at what happens as x goes to negative infinity. Oops, still positive there, sorry. Now for this, it's helpful to remember what y equals e to the x looks like. As x goes to positive infinity, we take e and raise it to a large power. We get a large number. The x values go to, or the y values go to positive infinity as x goes to positive infinity. But as x goes to negative infinity, the y values on this graph approach the x-axis. So the y values approach 0. So when we compute the limit as x goes to negative infinity, this term goes to 0 and this term goes to 0. So we end up with -1 divided by a large negative number. Negative divided by a negative is a positive, but 1 divided by a large positive number is going to give us a 0. So we have y equals 0 as a horizontal asymptote of that graph as well. So the function's going to approach y equals 0 as x goes to negative infinity on the left. And then the function approaches positive, y equals positive 1/2 on the right. let's graph this function and the two asymptotes, and hopefully the function's graph will confirm that those are our horizontal asymptotes. All right, so I'm not actually sure where I stopped recording. We were looking at the graph of this function here. And I was just trying to summarize this. We've talked about all of these limits at infinity for these functions. This had two horizontal asymptotes. This had infinite an infinite limit as x goes to plus or minus infinity. The y values go to positive infinity. And with this one, the y values go to 0. But there are some interesting features here with the vertical asymptotes. So we might talk about that in another video.